Now that we've defined additive manufacturing and how it can be used, let's understand why it's truly important. In other words, why should we think differently using AM? Now look around you and think of all the things that were made in factories, products from simple to complex, and imagine what it takes in terms of investment in infrastructure and time to go from the raw materials to the product arriving in your hands. I also teach the largest manufacturing class on campus at MIT, and every September on the first day of class, I ask the students for their definition of manufacturing, and then I give my definition of manufacturing as value at scale. This definition applies to bare necessities, food and water, to the most intricate electronics and advanced systems, such as automobiles and aircraft that contain thousands of parts, both mechanical and electrical. And to bring those products to market, to not only bring improvements in our quality of life, but also to bring a profit to the manufacturer. We have to manufacture in large quantities because of the investment in tooling and machines, and also the investment in design and scale-up that's needed for the producer to reach the marketplace.
Because 3D printing is unconstrained by traditional forming and machining methods, it introduces a lot of potential for savings. I mean, if you go back to aluminum billets, there's a whole bunch of energy that's put into mining bauxite and creating aluminum. And then you have to give it material properties, roll it, and then you start cutting it up into parts and pieces. There's all of these steps that happen when you start really thinking and considering the life cycle of a traditionally machined part. And manufacturing from an additive perspective can really shorten that flow.
So that's why additive manufacturing is different. And further, it's widely said that AM has a flat cost per part versus volume curve. In other words, the cost per part is the same whether you produce a few or you produce many. Now that's not strictly true, but it's okay for the moment. And for many years, the cost equilibrium point between a traditional route, such as making a part by machining or injection molding, and 3D printing it has been advancing, moving to higher quantities. And this will continue to advance, no doubt about that. So we can always compare the cost of making the same part by, say, additive manufacturing versus machining, but we can of course also leverage the design freedom that AM gives us. A great example is this bracket for an aircraft application that was put out as a challenge by GE several years ago and got solutions from around the world. The challenge was to come up with a design for AM that saves weight and material, and the winning result among many really cool outcomes is shown here. So for these and other designs by additive manufacturing, does complexity really come for free? That phrase is often used in the field, and I'd like to probe it in a bit more detail. So to do so, let's consider this series of parts. The parts from left to right on your screen have increasing complexity and the same external volume, or the same bounding box. The simplest part here is a simple block with a single hole machined in the center, and the parts progress in complexity. An intermediate complexity has features of different shapes and sizes, all machined from the same orientation from the top down. And if I ask an established machine shop to make one of each of these parts, I find that the cost increases with complexity. Obviously, because to create more features and remove more material by machining, I need more machine time, and I also need more involved machining operations and expertise. But if I look at the cost of 3D printing, in this case, selective laser melting of metals, one specific process, we see an opposite trend. The cost per part actually decreases with the complexity of its shape. So for a more complex design, albeit within the same external bounding box, I need less material, and I also need less machine time to build the part using additive manufacturing. Now if I compare the 3D printed part of the same complexity to the machine part here, we see some important differences. For instance, the surface finish of 3D printing is not as good as machining, so perhaps to make this comparison exact, I need to do some other processing on my 3D printed part. But nevertheless, if I use 3D printing, I can access further complexity than I ever can with machining. And without changing the configuration of the machine, I can build features from different orientations. So here are two 3D printed parts, and this one is somewhat more complex because it has slots oriented from the side. Or inside this part, if I opened it up, it's solid from the outside, I might find lattice structure on the inside, because this is further complexity that 3D printing can realize. And this could reduce the weight of the part, and in many ways further increase its performance, and perhaps further reduce the cost of producing it. And these charts show real data from machine shops that we queried just recently. And not only are these trends fundamentally different, but they also cross. In other words, there's an equilibrium point that says it's already less expensive to make such a part by 3D printing than machining if it has a highly complex geometry. So the value of unlocking that design space is both in cost and performance. And even more so, the most complex geometries in this example, that highest complexity index with the internal lattice, cannot be made by machining. So in a way, not only is complexity free via additive manufacturing, but it's in some words more than free. You can make complex parts for a lower cost than you can make simple parts.
For such a long time, half a century, we have been fabricating parts and tools and components in a similar fashion, where we subtractively remove material and we design it to the best of our abilities, but cost and complexity are traded into that equation, and it does constrain what you can do. With 3D printing, so many of those constraints go out the door. You can use software now to optimize where you put material. And you can only use the minimum amount to meet your stress and strain requirements, and the shape that you might get might be something totally organic, like a spider web or a bone structure. It's patterns that you would see in nature that are now going to be possible for our entire engineering team. So we'll be able to make that part, and we won't have to pay for that extra complexity.
A beautiful example of complexity becoming simplicity is this brake caliper. It's for a Bugatti, a high-end car, and this is a production part made to improve the performance of the brakes while reducing the weight. While Bugattis are really very high-end cars, the mainstream automotive industry is already preparing for and investing in metal 3D printing because its economics are going to get a lot better in the coming years. AM can also let us consolidate multiple parts. This is an antenna for radio frequency or RF beam steering made by a company in the US. Previous designs, like shown in the drawing here, had dozens of parts, but their new design has just one part. And you could only make this design by 3D printing, and it has improved performance, and this performance can be predicted by advanced RF simulations. Next, this is from Robot Bike Company in the United Kingdom. They make custom mountain bikes that combine carbon fiber tubes, which are very strong in compression and also lightweight, with 3D printed metal joints. The combination of these two processes and materials lets their product be possible and also lets them customize the bikes to individual riders by cutting those tubes to length and custom 3D printing those metal bracket junctions. So for these and other reasons, we see implications emerging over the product life cycle, from the first concept, the first idea, to the end of the product's life. Things as simple as Frito-Lay 3D printing plastic potato chips, believe it or not, as prototypes to test with their customers, to Mercedes-Benz, which is producing metal housings for temperature sensors for their Unimog vehicles, which are designed to last a long time and undergo very harsh conditions around the world. And as a result, it needs service from time to time, and they're fulfilling this need later stage in the product life cycle. And between the beginning and the end comes the heart of the product life cycle, which is mass production. Today there's rapid innovation happening in additive manufacturing to enable that mass production, and this includes improved machines and processes, lower cost and higher performance materials, and integration of AM with the workflow of product design and factory operations. Many challenges remain, but we're still gathering the momentum and resources to address those. And for these reasons, if we go back to my definition of advanced manufacturing as value at scale, I think we can, in some ways, redefine the axes by which we judge the viability of a manufactured product. The three axes here now are volume, the number of parts we make, customization, the customization of the product to the user, as well as complexity of the part geometry. So to keep it short for now and get back to this later, I believe we can envision viable manufactured products at any point in this 3D space, all the way up to the apex, where we can create entirely new products and business models, and also engage the customer in the design process and in the supply chain in exciting and valuable new ways.